We're getting down to the last talk of the symposium here. And our last speaker was going to be John Rakoven, but as Anne said yesterday, he had a bit of a biking accident, couldn't make it up here. And our hometown hero here, Phil, was kind enough to step in last minute and help us out. And Phil is our last speaker today. He perhaps doesn't need any introduction, but I will introduce him anyways. Phil is a lifelong mineral guy. He's been in the world of dealing for quite a while. He operates Persson Rare Minerals here in Denver. I'm sure all of you have seen him at shows. He got started actually in the area that he's going to tell us about today in Franklin, collecting fluorescence, and has since then he's done degrees in geology, economic geology. He knows everything about the St. Peter's Dome area. Has done a lot of stuff down there. Done a lot of stuff on rare earth elements and minerals, and just rare minerals in general. And with that, I'm going to turn it over to Phil, who, as I said, is going to tell us about the Franklin district.
Alrighty, thank you, Ben. So I want to congratulate everybody on making it to the end of the symposium. We're here. I am the final talk, so thank you for sticking around for me. And hopefully this will be interesting and entertaining, and I'll try not to go too long so you guys can get off on your day. So we're going to be switching subjects a little bit and going from Russia and Germany over to New Jersey to talk about Franklin. And most of you in the room probably have heard of Franklin to some degree. It's one of the more mineral famous places in the world. As Ben just alluded to, it was sort of my introduction to geology and mineral collecting growing up. So it has a near and dear place in my heart. And this talk is really meant to be kind of an overview on Franklin and Sterling Hill, the deposits, the minerals, the history, a little bit of fluorescence, and hopefully get you excited to visit if you've not been. So where are we located? So we're in northwestern New Jersey, about 65 kilometers from New York City, kind of in the northwestern corner of the state of New Jersey. And essentially, we're talking about two different mineral deposits, the Franklin mine and the Sterling Hill mine. And you can see that they're located fairly close to each other there. So a little bit about Franklin and Sterling Hill. These are two of the world's most complex and unique mineral deposits. They're very high grade. They average 22% zinc, which is sort of unique in the world, as far as I know. These are zinc, iron, and manganese deposits. And they were mined primarily for zinc. They're situated in the northwestern part of New Jersey, as we just said, in rocks that are Proterozoic age, and they have an amazing abundance of mineral species. There's 359 mineral species known from the Franklin Mining District. 71 of these are actually type locality species, which is pretty amazing. And 81 of them fluoresce under ultraviolet light, which is mineral collecting beginning about 300 years ago. Dutch settlers in the late 17th century actually noted the occurrence of these deposits, and it's possible that there was even Paleo-Indian activity happening before them. So a little bit more about the setting and background of Franklin. So the Franklin mine closed in September of 1954. The Sterling Hill mine operated quite a bit later and closed in early 1987. Thankfully, there are two world-class mineral institutions in the district. One is the Sterling Hill Mining Museum, founded in 1993 in Ogdensburg, and the other is the Franklin Mineral Museum, which was founded in 1964. There's also two great mineral shows, which I'm going to speak a little more about at the end of the talk. One is in April, and the other is in September, that happens every year. And research on the deposits is still ongoing. They're still very enigmatic, and the petrogenesis and origin of these deposits is still very much kind of under debate, you could say. So a little bit of a geologic overview. These maps are actually from a very old publication from 1868, but I think they're still very relevant, and they nicely illustrate the geology of the district. So basically what we're looking at here, the kind of yellow tan unit, that is the Franklin marble, which is a metamorphic rock, metamorphic marble. The green is the zinc deposits, and you can kind of see them there. This is the Franklin deposit, this kind of hook-shaped body here, and this is the Sterling Hill deposit, which is also kind of a fish hook shape. And you can see on the left here, we have the Cork Hill gneiss. This is a Proterozoic gneiss. And on the right, we have the Kittatinny limestone, which is a Proterozoic limestone. A little bit more geology here before we get into pretty mineral photographs. So again, the geologic setting, we're kind of sandwiched in between this gneiss and this limestone with gneiss on the other side. And we're in this little band of marble. And what's worth noting here on the right, this is from Palache, 1935, classic publication on Franklin, is that you can see these cross sections of the ore body. And in cross section, that fishhook shape of the ore body now looks kind of like a golf club. You can see it's dipping fairly steeply, about 55, 60 degrees, and it kind of fattens at the bottom and has this little bit of a hook shape. And as I'm going to talk about in a minute, part of that is an artifact of the fact that this deposit originally formed on the seafloor in what we call a sedimentary exhalative type lead zinc deposit, and then was metamorphosed at pretty high pressure and temperature conditions. So the Franklin mine has a 250 plus year history of mining. The workings were consolidated under the New Jersey Zinc Company back in 1898, and the mine closed in 1954. So a very long history of operation. You can see these photographs here showing some of the surface workings. This is the Palmer Mill. This is looking at the Buckwheat Hill and Buckwheat Mine here. So lots of activity, very long history of mining activity over the years. The Sterling Mine also had a very long history. It was actually first noted by Dutch settlers in the early 17th century, and this is because the west limb of the ore body actually outcropped at the surface. And minerals like willemite and franklinite and zincite tend to weather pretty readily and create this spectacular outcrop. So this was first mined for iron and zinc back in the 18th and 17th century, and then later for zinc only. It was closed in 1987, so you can see a little more modern head frame here, dating from the 70s. And now it's part of what's called the Sterling Hill Mining Museum. So how did the deposits form? So we alluded to this a little bit in a previous slide, but we think these are originally what we call sedimentary exhalative type lead zinc deposits. Oops, sorry about that. Going into a tunnel here. These originally, we think, came from what we call black smokers. And some of you are probably familiar with this concept. These are basically hydrothermal vents on the seafloor where fluids that are rich in lead and zinc and other metals are basically coming out of these seafloor vents in a rifting, a spreading kind of environment. And this was in the Mesoproterozoic period, so about 1.25, 1.3 billion years ago. These deposits were associated with limestones. That's very typical. And also some synchronously deposited bimodal volcanic rocks, things like rhyolite and fibolite once they were metamorphosed. And then what we think happened after that is that basically this whole package of rocks was metamorphosed at pretty high pressure and temperature conditions. And that led to the mineralogy that we see today. So a little bit more about how the deposits formed. So at 955 MA, so right around 1 billion years ago, this entire rock package, including these seafloor lead zinc iron deposits, were subjected to granulate facies metamorphism. So this is pretty high temperature, high pressure. This is a minimum temperature about 760 C and pressure of about 5 kilobars at a depth of maybe 11, 16 kilometers. And it's interesting, in addition to the metamorphosis, to think about the occurrence of some of these calcium silicate units, what we might call skarns, also dikes that are intruding and cross-cutting the ore bodies, some of which are a fair bit younger. This is very important when we think about the development of all these rare exotic minerals, in addition to the minerals that are more kind of primary in nature. And we'll talk a little bit more about that. So why do we have such an incredible enrichment of all these mineral species, right? It's interesting to think about what are some of the factors that led to this incredible diversity and enrichment of minerals, especially fluorescent minerals. So obviously the metamorphism was a prolonged, relatively complex event, and that not only converted the primary sulfides into the weird assemblage of silicates and oxides that we see, but it also created a lot of these skarn type minerals and calc-silicate minerals, which is where we get a lot of our weird fluorescent species at Franklin. Later, this whole area was intruded by pegmatites, both sodic and potassic, as well as things like diabase dikes. And these created more complex mineral assemblages and more weird stuff. So, a lot of our spectacular fluorescent minerals, the so-called lead silicate species like hardystonite and esperite, these were the result, we think, of this later intrusive and contact metamorphic kind of process. So one more slide before we get into some nice photos here of mineral species. So in addition to the two things that I just talked about, we also know that the deposits were tectonically deformed quite a bit. So they were folded isoclinally. This means almost in a 90-degree, were folded very intensely, and deformed associated with the metamorphism. And particularly at Sterling Hill, this created large zones of what we call myelinitized ores. So some of you know what a myelinite is. That's an extremely tectonically deformed rock showing plastic deformation. And we can even see this under UV, which is pretty amazing. And I'll show a photo in a minute that illustrates that. We also know that this really unusual, weird geochemistry was a result of a certain kind of geochemical condition. So we're highly enriched in zinc and iron and manganese, but also depleted in lead and sulfur, meaning that we don't get a lot of sulfides. So rather than having galena, we have willemite and franklinite and zincite as our primary ore minerals, which is really interesting. And sphalerite is there, but it's actually pretty uncommon. So, there's also some isotopic factors, but this geochemistry is fairly unusual for this deposit type, and it's a big reason why we have the weird mineral assemblages that we see there. So this is a pretty spectacular photo showing the surface exposure of the east main of the Sterling Hill ore body. This was taken back in 2008, and basically what you're seeing here is the outcrop of the ore body here, that's about 25 meters tall, is being lit up with high-powered UV lights, and the green stripes are willemite, and the red is calcite, which is basically the host rock of the deposit. And this is pretty incredible because not only does it show the amazing fluorescent properties of the ore deposit, but it gives you an idea of scale and also some of those kind of paragenetic features like the sedimentary bedding and the deformation that I just talked about. So fluorescent minerals. So fluorescent minerals were first noted at the Franklin mine a really long time ago, the early 20th century, when poor electrical connections of these so-called knife switches underground actually emitted sparks and electric arcs. And as you know, there's a UV component of this electric arc. And the miners probably thought they were going crazy when they first saw this because they would see flashes of color on the wall because of the UV component of these arcs. And that actually led to the development of a so-called arc lamp for fluorescent minerals. This was a predecessor to the modern UV light for mineral fluorescence. And this was actually used by the New Jersey Zinc Company for ore monitoring because one of the main ore minerals, willemite, fluoresces so brightly, and also kind of as a metallurgical tool. And that was used all the way up until the 1980s, kind of like fluorescence is used in diamonds and other gemstones for sorting and quality and other purposes. So we didn't see the development of low-cost portable UV lights until the 30s and 40s. But once that happened, that started a whole new trend in mineral collecting at Franklin, where the fluorescence really took off, and that ultimately led to over 80 different fluorescent species being identified there. And this actually stimulated the New Jersey state legislature to declare Franklin as the fluorescent mineral capital of the world back in 1968. So why so many fluorescent minerals? And also a little bit of an overview on mineral fluorescence. So this diagram here kind of goes over what happens when a mineral fluoresces. I'm not going to go over this in detail because we have folks in the room here who know far more about optical phenomena with minerals, and I'm not going to embarrass myself by trying to explain this. But essentially, fluorescence is an optical phenomenon where you have excitation and then emission of a photon and then decay back down to a lower energy state. And this can happen by a bunch of different mechanisms. But at Franklin, it's important to note that a couple elements, particularly manganese and lead, are important activator elements and things that we think stimulate fluorescence, and also things that lead to the abundance of fluorescent minerals at these deposits. And this is kind of a neat photo here. This is, I believe, George Catlin, who was a mine captain back in the 30s. And here he has a pile of fluorescent minerals under one of these arc lamps. And we've obviously come a long way since then. Here's another vintage UV light being used actually for ore control at the mine, probably back in the 40s or 50s. So now we're going to kind of get into the minerals of Franklin, and we're going to talk about the fluorescent and non-fluorescent species. I want to start off with some of the major ore minerals. Franklinite is a mineral that, if you're familiar with one mineral from Franklin, this is probably the one you've heard of. It's the most important ore mineral, and it's actually a member of the spinel group. It forms a series with magnetite. It's a zinc iron oxide. And what's interesting is that it's such a simple chemistry, but it's basically the only significant locality in the world for this species, and it's also the #1 ore mineral. So it's pretty rare where you have that kind of situation at any big ore deposit. It typically forms these very nice octahedral crystals. Here's a very large one from the Canfield collection in the Smithsonian. Here's a nice one from my friend Peter Gingrande's collection. Nice sharp octahedron. Some more examples of franklinite. You can also have sort of modified dodecahedral forms like this. You can have very complex morphologies. Franklinite is isometric, it's cubic, so you get all the modifications that you would expect in an isometric mineral. These combinations with brick red willemite are very classic and sought after. And this is a very typical assemblage for both deposits. Willemite is the #2 most important mineral. It is a zinc silicate, and willemite, unlike franklinite, actually does occur in many other deposits in the world. I would argue that this is volumetrically and also in terms of specimens the most important occurrence. But willemite is distributed across many deposits in Africa, also the Southwest US. But at Franklin, we see willemite in every single color, every single association, as massive specimens, as ore specimens, all kinds of stuff. These are some photos I took when I was at Harvard about a decade ago, where some of the best Franklin minerals are housed. And a little bit hard to see here, but these are beautiful, long prismatic crystals. These are so-called trotter willemite specimens, where you have this interesting matrix, and these are actually gemmy crystals. So the crystals can be up to 20 inches, which is pretty impressive, and there's a huge range of different colors that occur in willemite. So this is kind of fun. This is a box here that's now part of the Harvard Mineralogical Museum, and this belonged to a gentleman named Lawson Bauer, who was the New Jersey Zinc Company chemist in the early 20th century, and he actually put together, this set as a way to fool and test visitors. He would have students come and visitors come, and he would show them this box and say, tell me what minerals are in this box. Well, it was a trick question because they're all willemite, but it shows the amazing color variety of just one mineral from Franklin. And it's pretty cool. This is actually still preserved today at Harvard, showing all the variety of just one mineral species. Some more examples of willemite. These are very rare and prized, these gem quality crystals. There have actually been some fabulous cut stones in colors ranging from orange to blue to yellow of willemite from Franklin. You can actually see a few here at the Smithsonian collection on exhibit, these gem quality faceted willemites. These are extremely sought after on the rare gem market. This is sort of a poor photo, but this is a very high quality piece. And then this is more typical. This is a typical ore specimen here of this kind of shot put style willemite grains in a matrix of franklinite with some zincite. One more photo of just the color variety in willemite here, showing mostly massive specimens, but colors ranging from green to yellow to blue, gray. There's all kinds of sulfur yellow, apple green, tutti frutti. There's a million different types of willemite from Franklin. And needless to say, all of these fluoresce very nicely under UV light, shortwave UV light. So speaking of fluorescence, here is the classic Franklin fluorescent combo, so-called red and green. And here you have the willemite fluorescing this brilliant green color under shortwave, and you have the matrix as calcite fluorescing a red color. This material is locally termed red and green and can still be collected on the dumps. Going rate for this material used to be $1 a pound. I've seen it as expensive as $20 a pound or more in Tucson, but that's kind of an anomaly. This is still, I would say, if you're into fluorescent mineral collecting and you want to build a fluorescent collection on a budget, this is some of the more affordable, available material that you can get. And everybody should have a specimen in your collection if you're into fluorescent minerals. So here's a nice case of red and green from the George Pullman collection, just showing the variety of patterns, colors, associations. It's really infinite, right? All kinds of cool shapes and veins and, myelinitic textures, you name it. So the final ore mineral before we get into some of the more unusual species is zincite. And again, zincite is a type locality and really the only significant locality in the world. Some folks are familiar with the Polish zincite crystals. Those are not natural. Those form originally in a smelter chimney, and now I think they're being synthetically created in a flux in a lab and supposedly still marketed as being from the smelter. But anyways, those are not natural. Those are synthetic, they're gem quality, they're transparent zinc oxide. These are natural, and this is the only place in the world where you get zincite. Again, very simple chemistry. It's basically nominally zinc oxide with some manganese and iron substitution. But it's the only locality in the world where you get high quality crystals, and they're very sought after by collectors. This is a specimen here on the left, photographed by Rock Currier, about a 1-inch crystal. These are on display at the Smithsonian, actually cut gems, which are extremely rare from Franklin. And this is a large specimen here that was on display in Tucson about 10 years ago. Another case just showing the variety of zincite, just like willemite and franklinite. Even in massive specimens, you have an amazing variety of associations, of forms. There's this so-called lenticular zincite like this, which is a product of deformation and maybe some fluid immiscibility in the ore forming process. That's pretty interesting. So lots and lots of variety. So now we're going to get into the fluorescent species, and this is where things really get colorful. Franklin has a bit of a reputation for being ugly and massive, and I have to concede that's true, even though I love Franklin. Minerals are pretty darn ugly, and it's really only when you put them under UV light that their amazing quality and uniqueness kind of starts to jump out. So we're going to go through some of the fluorescent species here and touch on the major ones and then talk about a few of the less common ones. So hardystonite is another species that's basically unique to Franklin. It's the only worldwide locality. It's not found at Sterling Hill, and it is a calcium zinc silicate. So pay attention to this chemistry as we go through the following species here. Think about this chemistry, and you're going to start to see some overlap and some commonalities as far as mineral chemistry. So this fluoresces this nice purple color, typically associated with willemite, with calcite. The orange here is a mineral called clinahedrite, which we'll talk about in a minute. But hardystonite, thankfully for collectors, is pretty abundant at Franklin. And it's tough to field collect, but if you get lucky, you can still find some on the dumps. And it has this wonderful bright purple fluorescence like this. So here's another couple of hardystonite photos, again, showing the association here with clinahedrite. You can see a nice association with esperite, which is a chemically related mineral. Sometimes you have this kind of wispy intergrowth of esperite and hardystonite, which can be very attractive together. Speaking of esperite, esperite is probably, if you had to pick one species that's the king of fluorescent minerals from Franklin, it's probably esperite. It's been sought after for many years. It was originally called calcium larsenite in allusion to Esper Larsen, who I guess has two minerals named after him. I believe he was at Harvard. Carl could tell me for sure. And he worked on Franklin along with many other Harvard folks of that time period and described some of these species. So just like hardystonite, Franklin is the only worldwide locality for esperite that I know of. I think there's a prospect in Bolivia that produces microcrystals, but this is basically the only important locality. And it has this brilliant yellow fluorescence, very, very bright yellow fluorescence under shortwave UV light. And when we say shortwave, we typically are referring to around 254 nanometer light source, something like that. Whole case of esperite here from the George Pullman collection. Just beautiful specimens, very bright, very showy, very sought after by fluorescent collectors. And lots of different associations here with esperite, as you can see. One more photo of esperite, because why not? Just showing some of the associations. You can see clinahedrite, you can see hardystonite, you can see calcite. And what's really sought after when it comes to esperite specimens are the so-called 5-color specimens, and we'll show one of those in a minute. So another species that's typically associated with the two previous ones is clinahedrite. This is another calcium zinc silicate. You can see it's hydrated. There's one water hanging on there. And again, Franklin is essentially the only location in the world for clinahedrite. It can form small kind of amethystine crystals. This is a very fine example here, photographed by Rock Currier. These are very sought after and very rare. But typically it occurs as a coating on hardystonite. And we believe this is actually an alteration on hardystonite. And what's nice is you have the purple hardystonite, and then you have a thin film of this clinahedrite that's fluorescent this nice orange color. And it makes for a very attractive combination. And these are pretty attainable, I would say, on the fluorescent mineral market. Margarosinite is another highly sought after fluorescent species. It's not unique to Franklin, but it's definitely the globally most important locality. It also occurs in Sweden in the Långbahn deposits and some other deposits in Sweden. Again, look at the chemistry. It's a lead calcium silicate. And again, lead silicates seem like they wouldn't be that rare, right? But globally, they're actually pretty unusual. To get lead silicates, you know, in general, geochemistry, thermodynamics favors the formation of lead sulfides or lead sulfur salts, right? Forming lead silicates is a little more atypical. You need the right conditions to do that. So at Franklin, thankfully, the lead silicates are pretty abundant, and most of them tend to fluoresce pretty nicely. So this brilliant blue fluorescence, this is under shortwave, very bright. You can also have this kind of purplish fluorescence, pinkish fluorescence in margarosinite, which is sought after as well. Some more margarosinite specimens. Again, when you get these combinations with other fluorescent species, these just create fantastic fluorescent combinations. This so-called fish scale platy margarosinite here in daylight is very sought after as well and very sort of classic for the Franklin mine. And again, beautiful variety of fluorescent colors and associations. Roeblingite is a mineral that differentiates the true Franklin nuts from normal collectors. To a normal collector, this is probably one of the uglier, more blasé minerals on Earth. It literally looks like a chunk of coconut, but this will get fluorescent Franklin collectors foaming at the mouth. The going rates for these specimens are obscene. A little specimen that looks like a busted piece of coconut the size of a cookie will sell for thousands and thousands of dollars. So again, this is what separates the true Franklin crazies from the normal collectors. But it's a very rare mineral. Again, you can see here it's a lead species, but here we're actually talking about a sulfate, a hydroxide sulfate, and it's, I guess, a silicate as well. So a very complex mineral, and it occurs in this sort of complex assemblage with minerals like Hancockite and willemite and barite and clinahedrite and lots of other things. Has this very characteristic kind of cherry red fluorescence under shortwave UV. Couple more roeblingite specimens. This is a very fine piece here on the right associated with Charlesite, which is named after Charles Palache, and also manganaxonite, making for a very attractive fluorescent combination. There's also a series of unusual apatite group species that occur at Franklin. John Baumite, this is named after Jack Baum, who was the New Jersey Zinc Company chemist for many years at Franklin. Cuspidine is another rare apatite group species. And Turnerite. Turnerite is also known from the ZCA mines in upstate New York, St. Lawrence County. But all of these are apatite group species. They're Arsenian apatites for the most part. And they have this characteristic kind of orangey fluorescence, again, under shortwave, that's very attractive and makes them very collectible for Franklin. Wollastonite is another mineral that, again, very common species, right? This is literally a rock-forming mineral in parts of the world. This is the only place in the world where a massive that would otherwise be worth the ore value is selling for thousands of dollars. And this is why that is, because there's this incredible fluorescent response to the Franklin and Sterling Hill wollastonite. And wollastonite is so famous from Franklin that it's even been sub-characterized into different finds. So this is the so-called first find of wollastonite. This was back in 1944. And basically, this was just one pillar of low-grade ore close to a pegmatite. This is about the 600-foot level of the Franklin mine. They found, I don't know, a few hundred pounds at the most of this material. And this is highly sought after on the fluorescent market. If you had to pick one fluorescent combination from Franklin that people are looking for, this is the one. And this is a huge specimen, about 40 centimeters across. This is on display at the Franklin Mineral Museum. And just very bright, very attractive fluorescence. You can see there's some hardystonite, there's some willemite, there's some calcite matrix there. So this is the so-called second find. This was found a year later, 1945. On the 900-foot level, a little bit of a richer orange fluorescence, also very attractive, also very hard to get. And then finally, the so-called third find. This is a little more available. This is a nice three-color combination. If you get really lucky, maybe you'll find a piece on the modern dumps. But basically, you've got orange fluorescent wollastonite, you've got creamy fluorescent barite, and then you've got this calcite matrix, making for a very nice combination. So wollastonite also occurs at Sterling Hill. And it's probably equally abundant to Franklin, but it's much more abundant as far as surface collecting. So finding a wollastonite specimen on the dumps at Franklin these days is probably almost impossible. But if you go to Sterling Hill, you can collect some nice wollastonite specimens, and they're also very attractive. Typically, you have this kind of starry night effect here of orange fluorescent wollastonite and calcite. You can also have this kind of more yellowish fluorescence here on the right. Nice case of wollastonite from Sterling Hill, just showing the variety and color from Sterling Hill. And again, you know, under daylight, these literally look like garden rocks, but it just shows the amazing transformation of the minerals from Franklin and Sterling Hill when you start looking under UV light. It's pretty remarkable. So we have to talk briefly about the so-called Parker shaft combination. So at the Franklin mine, there was a shaft that was sunk in the 1890s called the Parker shaft. And this was kind of the Shangri-La fluorescent minerals. And a lot of the really weird, unique, spectacular species from Franklin were found in the sinking of the shaft. And this includes things that often include color combinations of 5 or more different minerals under UV. And we think what was going on is that essentially the shaft intersected a zone that had a lot of late-stage hydrothermal alteration of the primary ore. And this was also the first major shaft that was sunk after all the previous mine workings were consolidated by the New Jersey Zinc Company back in 1898. So back when Harvard, for example, was kind of a locus of study of Franklin, folks like Frondel and Palache really studied this area and wrote quite a few papers and quite a few studies trying to unravel the paragenesis and the history of what was going on there. Palache in 1935 described this as so-called pneumatolytic alteration, which is a little bit of a dated term. This was reinterpreted by Dunn in the 90s and others as being a kind of a hydrothermal metasomatic process. We see this in lots of mineral deposits, elements to begin with, and so when we altered and remobilized those, we got an even weirder set of minerals. So these are the so-called 5-color specimens I was alluding to. These are pretty amazing. What you're looking at is a combination of hardystonite here, the purple, a little bit of clinahedrite orange, yellow esperite, red calcite, and green willemite. And to get all of these on one specimen, these are highly sought after, and they're very, very attractive. You also have some of these combinations of the more exotic minerals, the lead silicates like margarosinite, which is blue, manganaxonite, kind of reddish, and zanodolite, which is violet. I believe it's a sort of a zeolite species. Prenite and pectolite. Again, these are very humble minerals from most of the world, but at Franklin, they're very sought after, and they occur only in this kind of restricted zone in the deposit. And we have a little bit of willemite and then a little bit of clinahedrite as well. Here's another beautiful piece showing a combination of pectolite, prenite, margarosinite, and willemite all on one specimen. Very, very attractive color combination. To be honest, the only other place in the world I know that really produces this intensity and brightness of fluorescent colors, well, I guess there's a few places. One is Greenland, and I would say Greenland is probably number 2 after Franklin. The other is the Långband district in Sweden. And the third is much less well known, but I think has potential to maybe even, I wouldn't say eclipse Franklin, but equal Franklin. And that is a glacier in Tajikistan called Dara Epos, which is very hard to get to. You have to take a helicopter in there. It's in an area with hostile players and terrorist activity and stuff. So not as easy as collecting a Franklin, but has some great fluorescent minerals. But really globally, this is quite unique to get this kind of combination of fluorescent species. So we talked a little bit earlier about these deformation events and tectonic stuff. And this is really cool because you're looking here at a myelinitized ore sample that's actually sheared. So that fabric you're seeing there is a result of shearing and deformation of the ore body. And it's, in daylight, this is hard to recognize, but under UV, you can see this beautiful shear cross kind of deformation texture here. Hydrozincite is a relatively common species. This is the blue mineral here. It's a zinc carbonate and typically occurs on a matrix of the ore minerals. Zincite in particular can pretty easily alter to hydrozincite. There have been some new discoveries. This slide's a little bit dated because this is the last time period where I was really involved in Franklin. But genthelite was discovered back in 2002 at Sterling Hill. This is a zinc beryllium silicate. Fun fact, the type locality for genthelite is actually right here in Colorado, in Cheyenne Canyon, down by my master's thesis area. Anyways, we discovered genthelite in 2002 at a small surface outcrop. And this is pretty neat because, again, Sterling Hill has been studied for over 300 years and we're still finding new species, which is pretty cool. And genthelite not only occurs as nice little crystals in daylight, but it fluoresces this very nice green color under shortwave light. So these are some pieces that I collected back in 2002, 20 years ago. It's hard to believe. This was kind of a neat find. This was literally in somebody's backyard. Around 2003, I was in high school at the time. John Cianciulli, who was a curator, gave me permission to go literally dig in these people's backyard. I mean, this is suburban New Jersey. So those of you that don't know the area, this is not the wild western frontier. This is the New Jersey suburbs. So yeah, if you're not collecting on the mine dumps at the museum, you're collecting in somebody's backyard. And luckily, locals are generally pretty understanding and kind of get that there are important rocks in their backyard. But anyways, we dug and we found a really interesting group of minerals. We found this chlorophane fluorite that fluoresces kind of a greenish color and also phosphoruses. We found apatite, we found scheelite. Later on, a weird mineral called pyroxferrite was discovered, which has been found on the moon. So that was kind of interesting. Again, very ugly, humble looking mineral, but it goes to show what can be found if you just study the stuff in enough detail. A couple notable daylight specimens to kind of round out the mineral description part of the talk. We have to talk about rhodonite. Rhodonite's one of the most famous species from Franklin. Unfortunately, it's going to be hard to compete with the new Brazilian rhodonites coming out. But I would say for classic factor, these are pretty amazing. These are big, blocky, pink rhodonite specimens. They're opaque, but they're very well formed from Franklin. Hemimorphite is another mineral that was an important ore mineral, actually. This is an alteration of the primary ore minerals and occurred close to the surface. This is a big specimen here from the Ewald Gersman collection. Hodgkinsonite, this is a mineral that will get Franklin people excited. It's basically unique to Franklin. It is a manganese zinc silicate, and it occurs in these very attractive kind of pinkish rose-colored crystals. There's a nice example at the Smithsonian with some barite. Conite, this might be my favorite Franklin mineral. This is kind of one of the ubiquitous Franklin minerals. It's named after our very own Lazard Kahn, who is a Colorado mineralogist and mineral dealer. Kahn's tombstone down in Colorado Springs, which you can visit if you're down there, is a giant conite crystal. And I hope when I die, my tombstone is a Perssonite crystal. I think that would be pretty cool. So kudos to Lazard Kahn. He was an amazing guy. And this mineral was named after him. This is a calcium boron arsenate hydroxide, very strange chemistry, and basically unique to Franklin. There were some small ones found in China recently, but they don't really compare to these. This is about a 1-inch twin at the Harvard collection, and just really amazing, unique mineral to Franklin. So is the Franklin district played out, or is it still worth a visit? Well, I would argue that it's very much worth a visit, and I'm going to close out the talk with a little bit of a suggested itinerary if you guys want to consider visiting Franklin. So there's two shows, as I think I alluded to earlier. One is in September, the other is in April. And I'm going to give you a little bit of a suggested itinerary for the September show, which is coming up in just a few months from now. So the show is over the weekend of the 20th of September this year. So you can fly direct from Denver to Newark, New Jersey. That's easy. And it's about an hour drive from Newark, obviously asterisk depending on traffic, up here through Northwest New Jersey, which is actually very pretty. You know, New Jersey, as somebody who went to high school in New Jersey, I have to stand up for New Jersey for a second here. New Jersey gets a bad rap. And there are parts of New Jersey that are pretty gross, to be fair. But this part of New Jersey is actually beautiful. And the state has done a really good job of preserving open space, preserving parkland. It's actually a very pretty kind of almost pastoral area, which you would not expect. People think it looks like this, which mostly doesn't. But anyways, drive up to Franklin here, about an hour drive. And if you have time that afternoon, you can go to the Franklin Mineral Museum and you can do some collecting. There's a place called the Buckwheat Dump, which has been a collecting site for almost 100 years now. And it's full of interesting minerals. This is basically waste rock from the Franklin mine. I believe it's currently $10 plus $1.50 per pound. So very inexpensive. And you can go and you can collect some cool specimens on the Buckwheat Dump here and visit the Franklin Mineral Museum, which is one of the two famous museums. So there are some possible night collecting opportunities, depending on your interpretation of the law and how brave you're feeling. There are places to collect at night. Some of them involve sneaking under fences, yeah. But, you know, there are options. I mean, these are photos of different places. This is the so-called mill site. This is when it was actually open to collecting back in the 80s. People found fabulous stuff there back in the 80s. Currently, it's been sort of reprocessed and covered over by a nursing home and some other development. But, you know, be quiet and start digging a hole and you'll find some interesting minerals. Almost guarantee it. So Saturday, the first day of the show, and this show is really a lot of fun. This is an old school mineral show. It happens indoors in a school gymnasium, but it also happens outside. And I believe that might be our very own Alfredo Petrov there, who travels the world selling rare and ugly minerals. And he is set up there in the what we call the pond swap and sell. And this is really a throwback to how mineral shows used to be years ago. It's lots of deals, lots of affordable stuff, lots of local minerals. It's really a lot of fun. So definitely encourage checking that out. Typically, at the evening of the Saturday of the show, they have a night dig at Sterling Hill. And if you've never done this, this is an experience. So you actually here again are looking at a photo of the outcrop of the ore body lit up at night. This is about a 50-foot high outcrop. And you have never seen anything like this. No matter what you've done in the world with minerals or gems or anything, you have never seen anything like this. This is amazing. And I believe they still do this every year. I haven't been to this dig in about 10 years, but I believe this is still something they do every year. And you can collect minerals on the dumps. So the second day of the show, you can do some more field collecting at Sterling Hill. You can also go to the garage sale, which is something fun that they do at the Sterling Hill Mining Museum every year, where they have lots of deals on minerals. And once you're all mineraled out and your pack is full of ugly, heavy rocks, you can fly on back to Denver. So that is my talk on Franklin, and I'll take any questions if you guys have them.
Thank you, Phil. That's super cool. Are there any questions for Phil? Yes, we have one right here.
You mentioned on a few of them that they're fluorescent under shortwave UV light. Is the primary wavelength that the minerals here fluoresce shortwave, or is there some long-wave fluorescence as well?
So great question. So a lot of them do fluoresce under shortwave dominantly, but you know, the light technology has really changed that. So like the convoy lights that you might be familiar with now, the long-wave flashlights, most shortwave minerals will actually fluoresce to some degree under those lights. They're just not as bright. And again, because the lights are so much brighter than they used to be, it's been really interesting looking at stuff, for example, under the convoy, which is basically long wave. Lots of things fluoresce that weren't like traditionally considered to fluoresce under long wave. So, and the other advantage is that these convoy flashlights, to get a bright one cost under $100, and to get a similar shortwave is like, you know, $400 or something. So for people first getting into fluorescence, it's much more accessible, and you can just put it in your pocket, which is convenient. Caleb?
With on one of your slides, you said there could be an occurrence of spotlight. Would that end up being burned? Or?
Yeah, so that's a good question. That's a question mark at this point. It's material that I actually was part of collecting back in 2003, and unfortunately the curator at the time, Johnson Truly, passed away, and it kind of just was left an open question. It turns out, as you know better than me, these apatite species can be tough to distinguish, and the last I heard about the so-called Zweibite is it had been sent off for some more advanced XRD work and some other stuff. And it was kind of it was a question mark. But traditionally, all the apatite from Franklin that fluoresced orange was called sphaebite. But now that we've reanalyzed the stuff, it turns out it's more complicated.
You gonna do it?
Around next year, he said, John.
Yeah, sounds
Central
good.
Proto, maybe.
Oh,
Yeah. Any other questions for Phil? Anne has a
Anne?
question.
I'm super curious what the setup was like to illuminate a 50-foot rock face with shortwave UV. Like,
Yeah,
how?
so great question. So you can kind of, you can't quite see it in the photo here, but that gentleman there in the foreground, basically in front of him is a big array about the size of a pallet of high-powered shortwave lights, and those are aimed at the outcrop. And I can tell you, if you're anywhere in front of those lights or near those lights, you want to wear eye protection. The first time I saw this, I was like 16, and I was only out there for like 10 minutes. And I checked it out. It was amazing. And I woke up that morning about 3 a.m. and I felt like somebody poured sand in my eyes. And I couldn't sleep for like 6 hours. And that is something you really want to avoid. So safety note, if any of you are collecting with bright UV lights, please wear eye protection.
Thanks, Phil. Any other questions for Phil? Yes, Mike.
Phil, so we always thought of it as one deposit, but two ore bodies. You kind of said two deposits, but really it's, Franklin broke up. It was one ore body that formed and then it was faulted apart. And when the last few years of mining, they were actually mining underground a little more than halfway back towards Franklin because of the ore body trended, down dip.
Yeah. So I've heard.
So the Franklin piece was faulted up.
Mhm.
Okay, so that's and so then they postulated, they thought that this ore body actually continued. There was big tonnage of ore left when they closed the mine.
Yeah, so I've heard different interpretations on that, and you might know more than me on this, but I've heard that it's considered to be two separate deposits that form synchronously in the same manner. Because if you think about the seafloor, right? I mean, typically the way these VMS deposits form, which is basically what these were, is you have a vent and then you have lateral deposition and replacement of the seafloor sediments and also these things spreading out on the seafloor. So that could definitely happen at multiple vent sites. But given the complexity of the tectonic activity and folding and faulting, maybe these were originally joined. What I find a little perplexing if they were joined is how come you have so many species at Franklin that are unique to Franklin that don't occur at Sterling Hill, right?
Well, I think a lot of that has to do with the much greater abundance of pegmatites and dikes at Franklin than in the Sterling Hill area. You see almost no pegmatites, very little. But actually, like I said, they'd done some additional drilling and near as they could tell, looked like the ore body was at least going to get them almost all the way to Franklin if they kept mining for another 10 years or so. But
well, it would be a great PhD topic for somebody.
Yeah, no, I mean that was they did that drilling right near the end of the. But the other thing is the shape. It's got the same hook shape to it at both.
Yeah.
Both deposits.
I don't personally believe they were the same ore body, but we can debate it later at the micro meeting.
I have a question. So all the formulas, all the mineral formulas you were showing, there was no aluminum in any of those. Is there any aluminum floating around the system?
Yeah, it's a good question. I mean, so there's a lot of rock forming species and sort of calc-silicate species that have aluminum. Most of the ore minerals, it seems like, do not. And even a lot of these silicates, they're pretty simple chemistry. They're lead, calcium, zinc silicates. So yeah, I'm not enough of a geochemist to tell you why they were partitioned that way. But there are a lot of, my guess is that some of these calc-silicates, these are often higher temperature, right? And they incorporate things like aluminum first, and then the remaining stuff is a little bit depleted, perhaps.
Yeah, for sure. Yeah, makes sense. Cool. Are there any other questions for Phil? If not, yeah, let's thank Phil again.
Thank you, guys.